Hi, everybody. Well done for making it this far through NAB. I'm Gareth, Sylvester-Bradley, and this is my colleague, Jonathan Thorpe from NVIDIA. We are system software architects for NVIDIA's open platform for live media production and real-time AI. We're going to be talking about MXL, which, if you were here earlier, we've heard a bit about, and NMOS. NMOS is something that we've been involved with for at least 10 years, I think, and MXL and the rest of the dynamic media facility layers over the last couple of years. So just to set the scene, the AMWA, the Advanced Media Workflow Association, is made up of both customers and vendors, systems integrators, writing specifications for interoperability of network media devices. NMOS enables management of IP-connected video and audio devices and software applications. Activity groups develop the specifications openly, publish their work in progress on GitHub. Just to explain how NMOS works in current day systems, we imagine that we've got devices from multiple vendors, network devices. We want to be able to set up those IP media flows, ST2110 and other kinds of media flow. So what NMOS does is say, let's give each of those vendor devices an API which is able to describe what kinds of sender, receiver inputs and outputs those nodes have, and we'll define an NMOS controller for the control system that is able to interact, a client for those NMOS nodes. The other thing that's a key part of the basic NMOS ecosystem is an NMOS registry, and that's the thing that is going to make it easy for the control system to discover all of those different vendor devices. The nodes use the registration API to advertise themselves into the registry. The controller uses the query API to discover the available nodes and senders and receivers in the registry. And then it uses a connection API defined by NMOS to configure the senders and receivers of nodes to initiate the media stream. That's the basics of NMOS. You kind of see the NMOS logo there, and I think, to me, it's clear it comes from those separate vendor devices, those separate blocks, making up a network media system. What is MXL? So MXL is the media exchange layer of the dynamic media facility reference architecture, which we've heard a bit about this morning. It consists of these common IT layers with media-specific layers on top. It's designed for software native and cloud native environments. The media exchange layer is the first layer that sits on top of COTS infrastructure, and you can kind of see where the MXF logo comes from. It's that middle layer of the dynamic media facility. It uses direct sharing of media essence in memory on hosts. So rather than senders and receivers, we have writers that write essence into shared memory. And we have readers that can be configured to pick out a flow from shared memory. Again, the MXL SDK is being developed openly on GitHub. System with MXL-based things is going to be applications deployed on off-the-shelf compute, using the MXL SDK to access that shared memory and to be able to start writing and reading from shared buffers. If we squint, I think you can see the similarity between that and the kind of network IP flows that NMOS is designed to control. So things have moved pretty fast. The dynamic media facility reference architecture first version was published in the end of 2024. The media exchange layer became the project just 6 months or so later. We set up a joint task force between EPU members, customers, and the AMWA with both customers, system integrators, and vendors in November last year. And the MXL SDK reached version 1.0 in February, and the working groups of the JTDMF kicked off around the same time. Flow Connection Working Group defined the requirements for setting up connections between MXL applications, and that activity group kicked off in the AMWA this month. Hoping to move really fast, and so in a matter of weeks, we hope to have a draft specification based on work that many vendors have already done, proving the principle. There are some other JT-DMF working groups open to all EBU and AMWA members, focused on end-to-end timing, the deployment and management of resources on COTS infrastructure when we just deploy multiple applications from multiple vendors, making sure they all have guaranteed isolated slices of resources, CPU, memory, GPU, etc., as well as the flow connection, a business track, and a focus on security. Flow Connection Working Group is defining those requirements for how not just making connections between MXL readers and writers, but how those are discovered, how the connection is negotiated. So this NMOS support for MXL activity in the AMWA is aiming to find a very short, a one-pager best current practice specification for doing that MXL connection management using the existing features of NMOS, the IS-04 specification and the IS-05 connection management specification. The first draft will cover where MXL is right now for version 1.0, and future MXL functionality will be added to the specification in a agile update. So that will include things like supporting GPUs and other accelerators doing MXL, which will probably need a small amount of additional information at the flow connection management layer to ensure flows are replicated between the accelerators where they're written and the accelerators or system memory where they're read. That work, as I say, is also being done very openly, and the work in progress specification is already published, and you can go and look at it on the AMWA website and look at contributing to it. Again, that's in GitHub. So we're going to talk about putting that into practice, one of the POCs that we ran, and I'm going to hand over to Jonathan to talk that through and give you a demo of what we're doing. Thank you.
Okay, so we're going to show you a short video that demonstrates using NMOS to control MXL. Well, as we model them as NMOS senders and receivers, those MXL writers and readers. So in the demonstration, what we have is we have a media function. That media function will be controlling MXL writers and readers, and we're modeling those writers and readers as NMOS senders and receivers. The media function will register with an NMOS registry, and then we have a lightweight NMOS controller that uses the query API to discover the media function, and then uses the IS-05 connection API to do connections between the MXL senders and MXL receivers. So I'll talk a little bit about how we've achieved this. We've basically used lots of off-the-shelf things that are kind of freely available. So the media function itself, we've been using Sony's NMOS CPP open source code base, and we've modified it to support the latest draft version of AMWA IS-05, which is version 1.2, is currently in draft. We're using the MXL SDK's kind of reference MXL writers and readers, and we've got a small Python script that acts as a bit of kind of implementation glue, kind of connect the node to the MXL SDK writers and readers. The NMOS registry, that's a completely standard NMOS registry. Again, we've taken that from the NMOS CPP open source code base, and the controller is a slightly modified version of Sony's NMOS JS open source controller, again modified for the latest draft specification of IS-05. Okay, I'll get my caveats in. This demo was run on my laptop in my hotel room, so if the video performance of the video rendering isn't quite up to scratch, please forgive. But what we can see on the screen here is just the various parts of the system that we're running. So in the top left of the screen, we have the NMOS CPP registry. So as I said earlier, that's just a completely standard NMOS registry coming from Sony's open source software. In the top right, we have the NMOS node that we're using to model the MXL senders and receivers. In the bottom left, we have what we call the NMOS, the MXL NMOS bridge, which is a Python script that's just acting as kind of glue between the NMOS node and the MXL writers and receivers. And then in the bottom right, what we can see there is we're looking at the MXL domain. So as was mentioned in earlier presentations, the MXL flows are virtual files that sit on the file system. So as such, we can actually go and kind of inspect them. We can go and look at the file system to see those flows. Now, with the system in its kind of initial state, we have no senders that are active, therefore there's nothing flowing. So if we were to look into that domain, we would see that it was just an empty directory. There we go. Okay, so next on the video, we'll see opening up the NMOS JS controller. This is using the query API to talk to the registry, so we can see the MXL senders and receivers. We have video, audio, data senders, and audio, video, and data receivers as well. We can see the transport has been denoted as MXL. So what we want to do now is we want to connect some senders to some receivers. Well, before that, actually activate the senders. So we can activate the senders. So now that will have created MXL writers that will be writing to the MXL domain. And we can now see on the file system those virtual files are there. So the next thing we do is make that connection between the senders and the receivers. Which will happen soon. So in the controller, when we click on the receiver, we can see compatible senders, and we can just select one, do an immediate activation. The video starts flowing. We have more than one sender, so we can also connect the other sender to another receiver, which will happen in a moment. There we go. So here we just have a test card with the time in the top left-hand corner, which I think you can just see on the screen. And so all of this has been done using NMOS IS-05. And we can wire it up how we like. So actually what we could do is we could actually connect both receivers to the same sender. There's no limitation. So here we can see that both receivers receiving exactly the same video from a single sender. And so the thing to stress is this has all been done using a standard NMOS controller using the IS-05 connection API. What we're going to do now is just deactivate the deactivate the receivers. So with each receiver that's deactivated, it removes the rendering of the video. But the MXL float is still there on the file system. The senders are still sending. So what we can do is deactivate those. Finally, we can see that in the domain, it's empty. Everything's been cleaned up. So that demonstrates that kind of end-to-end flow from senders to receivers. Normally, people are told to don't try this at home, but actually, I'm saying do try this at home. If you want to be able to reproduce this demonstration, all of the resources are freely available. So we've been using NMOS CPP. The kind of modified versions are sitting on a pull request on the NMOS CPP GitHub. So you can get that code there, and also the NMOS JS modified version. There's a pull request on the GitHub for that you can also get. The little bit of Python that bridges the node to the MXL SDK is on my GitHub. Feel free to go and grab that. And then the MXL SDK is freely available, and we've been using the reference writers and readers that are part of that SDK. Other resources that may be of interest, the JT-DMF on the AMWA website. You can look there for other resources to do with that. And as mentioned earlier, the draft specification for the recommendations around how to do this MXL connection management in NMOS are rendered on the AMWA.tv website at that URL. Okay, I'll hand you back to Gareth.
Thank you, Jonathan. I think it's a convincing demo, very, short and sweet, and basically speaking, everything just works with the combining those current specifications. This implementation was, put together very quickly. Obviously, vendors are free to integrate this in whatever way they choose. So yeah, encourage you to look at this and participate. The JTTNF working groups are open to all AMWA and EBU members. The MXL SDK Technical Steering Committee calls are every week, and they're open to everybody to join and listen in. And yeah, the BCP activity group has kicked off, aiming to deliver a first version of the spec in just a few weeks. It's always part of the AMWA process to wait until we have multiple vendor implementations before the specification is approved and published in final form. I think we already have 2 or 3, but more implementations of both the kind of node side, the device side or the application side, and on the controller client side are always welcome, so that we're sure we've covered everybody's use cases. Thank you very much. Any questions?
Thank you for the presentation. There's one point I have a question about. I'm not sure it was the emphasis of the presentation, but I still found it interesting. You mentioned that in the next version of the standard for MXL, flows could be located on the GPU memory, and we could want to have some kind of information to give the reference to the host memory where it was coming from. You see, as a requirement for a flow to be in the GPU memory to have a reference to a host memory location where the same flow would be? I don't think it's a requirement, and I from my perspective, I think flow could be in the GPU memory, on the host memory, on another host memory. It could be replicated as described in the presentation from Vincent before, and be replicated between 2 hosts, between a host or GPU, or it could be not replicated at all, just on the GPU memory.
Yes. So flows are going to exist wherever the writer has written them. If it's a GPU-based writer, it's probably the first thing it's gonna do naturally is write it to GPU memory. If there is a GPU-based reader, we want it to be able to read directly from that GPU if it has access to the same GPU. If we have other readers which are CPU based, they are working in system memory, then we need a replication. So, and the same thing in all directions, right? So I think we're saying the same thing. And what we need from kind of the connection flow discovery point of view and the orchestration is that ability to know in the control plane, the orchestration plane, where those media functions are writing, where they are capable of reading from, in order to make the decision about which flows to replicate where. So the next phase of the MXL SDK to add that ability to support GPU memory or other accelerator memory, and to support inter-host setup. That information needs to go into the control plane that advertises the transport, so that the control system, the orchestration plane, can set up the right replication. So that will be, when the MXL step's done, the NMOS specification will have a few more parameters to make sure sufficient information is there to be able to do that.
Thank you.
Okay. Thank you very much, everybody.